Alright, in this video we review the properties of the exponential function where the exponent is imaginary. Here this I is the imaginary unit, that is I squared is equal to -1, and this t is a real variable. In particular, we first derive this Euler's formula starting from the Maclaurin expansion of the exponential function. And in the end, we prove this identity, where here this n is an integer. And when n is equal to 0, then this integral becomes 1. Otherwise, this is 0. And this will be important for Fourier series in later videos. Okay, let's start. First of all, we assume that you already know what complex numbers are. Okay, complex number, let's say z is a complex number, then it can be represented as x plus iy, where x and y are real numbers. Okay, for this complex number, we can define its absolute value as this square root of x squared plus y squared. And we define its conjugate, complex conjugate, as z bar, which is equal to x minus I, y. So we change the signs here from plus to minus. We can add, subtract, multiply, and divide complex numbers just like real numbers, except that we have I squared is equal to -1. Okay, so let's multiply this and this. Z and z bar is x plus iy times x minus iy. So if we expand this, we have x squared, let's say minus I xy plus iyx and minus I squared y squared. And I squared becomes -1. And multiplication between real numbers is, of course, commutative. So this and this will cancel. And after all, we have x squared plus y squared, which is equal to the absolute value of z. So this absolute value can be also written as z times z bar and square root of that. Now, from calculus, you should know that the usual exponential function with the real variable, x is real here, can be expanded as this. So sum n from 0 to infinity and x to the power of n divided by n factorial. So this is the Maclaurin expansion of the exponential function. Now let's extend this to imaginary numbers. So we replace x with it, where t is a real number. So this is an imaginary number. So suppose this Maclaurin expansion still holds for this it to the power of n factorial. So as usual, I squared is replaced with -1. So let's expand this more explicitly. So first we have 1 and it over 1 and I squared t squared over 2 factorial and I cubed t cubed 3 factorial and so on. So this becomes 1 it over 1 and negative t squared, and this one will be negative I t cubed 3 factorial, and the next one will be, so we have I to the power of 4, that's -1 squared, that is 1, so that is t to the power of 4 over 4 factorial and so on. So let's sort this out into a real part and the imaginary part. So the real part will be this, and so on. So all of the terms with even powers will be in the real part. So 1 minus t squared over 2 factorial plus t to the power of 4 factorial, and the next one will be negative t to the power of 6 and 6 factorial and so on. So that's the real part. And the imaginary part is this one and this one. So all the odd powered terms are imaginary part. So if we factorize I out, the first will be t, and negative t cubed over 3 factorial, and the next one will be positive t to the power of 5 over 5 factorial, and so on. And if you notice, this one is actually the Maclaurin expansion of cosine t, and this part is the Maclaurin expansion of sine t. So after all, we have this equality. E to the power of it is equal to cosine t plus I sine t, which is Euler's formula. Now, let's calculate the absolute value of this quantity. So cosine t is the real part and sine t is the imaginary part. So that is square root of cosine squared t plus sine squared t, which is equal to 1. And of course, the complex conjugate of this is cosine t minus I sine t. And of course, cosine is an even function, so cosine t is equal to cosine negative t, and sine is an odd function, so negative sine t is sine negative t. So this is equal to exponential of negative I t. So the complex conjugate of e to the power of I t is e to the power of negative I t. Next, we see this exponential function with imaginary exponent inherits all the properties of the usual exponential function with the real exponent. So for real exponential function, we have this relation. So exponential of x times exponential of y, where x and y are real, is equal to exponential of x plus y, right? So in fact, we also have this, let's say exponential of it times exponential of is is equal to exponential of it plus s. So let's show this. So this left-hand side is equal to cosine t plus I sine t times cosine s plus I sine s. So if we expand this, we have cosine t, cosine s, and the real part will be negative sine t times sine s. And the imaginary part, sine t times cosine s, plus cosine t times sine s. But using the trigonometric identities, this is equal to cosine t plus s. And this one is equal to sine t plus s. So this is equal to exponential of I t plus s. And we're done. Okay, the next property is this. For any real x and any integer, we have, for the usual real variable exponential function, we have e to the power of x to the power of n is equal to e to the power of nx, right? And the same holds for imaginary exponent version. So that is e to the power of it to the power of n is equal to e to the power of int. So let's show this. By the way, this left-hand side means this. E to the power of t times e to the power of t times and so on times e to the power of it. So we multiply the same factor n times. Okay? Now, let's start from n equal to 0. In this case, e to the power of t to the power of 0. Of course, this is, we multiply this 0 times, that should be equal to 1. When n is equal to 1, that's trivial, so that is just this, so it's trivial. Now, suppose, obviously we're trying to prove this by mathematical induction. For n equal to k, we have e I t to the power of k is equal to e to the power of I k t. So suppose we have this. Now, when n is equal to k plus 1, we have e to the power of t k to the power of k plus 1. So this is of course equal to e to the power of I t k times e to the power of I t. Okay, but by assumption, this part is equal to e to the power of I k t. But from the previous theorem, we proved that the product of exponentials, even when the exponents are imaginary, this is equal to e to the power of I k kt plus t, which is equal to e to the power of I k plus 1 t. So when n is equal to k plus 1, this still holds. Therefore, for any positive or zero, positive integers, non-negative integers, we have e to the power of I t to the power of n is equal to e to the power of I n t. So that's for non-negative integers. To prove this for negative n, first we note that e to the power of 0, which is of course equal to 1, is equal to e to the power of it minus it. And of course this is equal to e to the power of it times e to the power of negative it from the previous theorem. So therefore, e to the power of negative it is equal to 1 over e to the power of it. So from this, let's say e to the power of it to the power of negative n. Let's say n is a natural number, so that is positive integer. So this means 1 over e to the power of it to the power of n. But this is equal to 1 over e to the power of it to the power of n. But this inside this is here, this one. So that is e to the power of negative it to the power of n. Now this exponent here is, this power is a positive integer. So we can use the previous result. This t can be positive or negative. It can be whatever. It's just a real number. So we can use the previous result, and we have e to the power of negative it times n. And of course, this is negative int. And so for any integers, whether it's positive or negative or 0, we have this relation. Nt, and we are done. So we introduced this exponential function with imaginary exponent by using the formal Maclaurin expansion of the ordinary exponential function, but this behaves exactly like the usual exponential function with a real variable. So we can safely call this an exponential function. And we can differentiate or integrate this type of function just like we did for this ordinary exponential function. For example, let's say exponential of int. If we differentiate this with respect to t, then we should have in times exponential of int. And if we integrate it with respect to t, then we should have 1 over in and exponential of int plus some constant. Finally, let's prove this important formula that will become important in Fourier series analysis. Exponential of int dt, where n is any integer, is equal to Kronecker delta of n and 0. So that means this is equal to 1 if n is equal to 0, or equal to 0 if n is not equal to 0. Okay? First of all, when n is equal to 0, if we calculate this, that's exponential of 0. And of course, that's just 1. So if we integrate 1, and we have t from 0 to 2 pi, and that is 1. So 2 pi minus 0 is 2 pi, divided by 2 pi, that's 1. And when n is not equal to 0, then let's integrate this. dt. So that is 1 over in, exponential of int, 0 to 2 pi. Now, in, and so we have exponential of in times 2 pi minus exponential of 0. But this one is of course 1, but this one, exponential of in 2 pi is equal to cosine 2 pi n plus I sine 2 pi n. So n is an integer, so integer multiple of 2 pi is here. So cosine of such a number is 1, of course, and sine of such a number is 0, so that's 1. So we have 1 minus 1, that's 0. So we're done. If you want, you can visualize this on the complex plane. So real axis, imaginary axis. So 2 pi times n means we start from argument of 0, and 2 pi times 1 is 2 pi. 2 pi times 2 is again here. So that's always 1. And or negative 1 times 2 pi is of course 1. And so how many times you rotate, it's always 1. So this is the result. Okay, that's all for this video. See you later. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.